Hi, this is Tzvi Rosen, professor for MAC 2312, and I'm going to give some background today for Calculus 2. This is the first lecture in the course, just going over some things that tend to be helpful for this semester of calculus. Okay, so the first thing that I really want to encourage you all to avoid is not to make these two mistakes. So if you have two fractions, a over b plus c over d, please do not put them together like this, okay? You can see pretty straightforwardly that this is wrong if you were to take, for instance, let's say a is 1 and b is 2, and then you have c will be 3 and d will be 4. You add those together. And if you would think this would be a plus b over c plus d, this should be 4 over 6. And plainly, that is not what this is, right? This is 2 over 4 plus 3 over 4, which is 5 over 4. Okay. Similarly, a common mistake is if you have a over b plus c, people think you can distribute the numerator over the two parts of the denominator, so that you get a over b plus a over c. This is also plainly incorrect. Let's do another example. So if you have 1 over 2 plus 3, if you would think this is equal to 1 over 2 plus 1 over 3, well, we know this is equal to 3/6 plus 2/6 is 5/6, whereas this is equal to 1/5. Okay, so plainly, these two things are unequal. So please, please, please try to avoid making this mistake in your assignments. Okay. Okay, now let's do some review of exponentials and logarithms. So the first thing, e to the a times e to the b is equal to e to the a plus b. Okay, multiplying the exponentials means you add the exponents. And there's some pretty straightforward intuition for this. If you have e to the a, so that's, again, a can take any real value, or any complex value really, but any real value. But let's say it's taking an integer value, then we're multiplying e by itself a times. Okay, so this is a times. And then we're multiplying that by e multiplied by itself b times. So when we take it all together, this is, this is a plus b times. Okay, that's pretty straightforward. If you have e to the a raised to the bth power, then you multiply the two exponents. Okay, so again, this is also relatively straightforward. If we have e a times, and then we repeat that b times, so another a times, and we do that b times. Okay. Let's make that a little nicer. Then that ends up being a total of a times b repetitions of e. So this becomes a, b instances of e. Okay. If we have e to the minus a, that's given by 1 over e to the a. And one way you could think about this, we know that e to the a times e to the minus a equals e to the a plus minus a, which is just e to the 0. And when you have no e's, that's just the empty product, which is 1. So that means that e to the minus a is 1 over e to the a. 1 over e to the a. Okay. And recall this notation, which comes up sometimes. If we write exp of a, that's the same as e to the a. The only reason we'll do that is if we have a big expression, which we don't want to write in tiny script above an e, then we'll use exp instead. Okay. So let's do a few examples. If you'd like to give these a shot, you can pause the video now and try these out. And now we'll go ahead and do them. So we have e to the 3 times e to the 5. We add exponents. So that means we have e to the 3 plus 5. And we're squaring that. That's equal to e to the 8 squared. Okay, and when we have an exponential raised to a power, you multiply the exponents. So that's e to the 16th. Okay. Not too complicated. This next one is a bit more complicated. Let's say we want to combine all of the things in this expression into one exponential. Well, the first thing we want to do is we want to take e to the y squared raised to the y power. When we have an exponential raised to a power, we multiply the exponents, so that's e to the y cubed. And then we divide that by e to the 3y, but that's the same thing as multiplying by e to the minus 3y, which gives us e to the y cubed minus 3y. Sorry, let me just box this off. This is an equation. And then when we multiply by the next term, we get e to the y cubed minus 3y. In terms of x cubed, how do we put x cubed into the exponential? Well, x cubed, we can think of that as e to the ln of x cubed, or e to the 3 ln x. So the answer is, when we multiply that in, we get e to the y cubed minus 3y plus 3 ln x. Okay. We can box that. Box this one as well. Okay. Now how about this one if we have the exponential of 2x minus 3 over cosine x? So here we're trying to go in the other direction. We have something inside of an exponential and we want to break it up. So the first thing we do is we can break up the subtraction. So we have e to the 2x times e to the minus 3 over cosine x. Okay. And if I wanted to break that down even further, I could make this e to the x squared. That's one way to do it. And then we can put the e to the minus in the denominator so that it's e to the 3 over cosine x, which we could also write as e to the 1 over cosine x cubed. Okay. This is not the only way to write this. And if you were to be given this problem on an exam, it would be much more specific as to what it wanted. But this is one way to express this more complicated exponential in terms of less complicated exponentials. Okay, now let's talk about some logarithms. As you know, the logarithm is the inverse function to the exponential. And some important properties are ln of ab equals ln of a plus ln of b. Ln of a to the b equals b times ln of a. And ln of 1 over a equals minus ln of a. Okay. And these are all kind of versions of the exponentials, just in the inverse form. Okay. And here are some examples for us to work through. And again, you can pause your video if you want to give these a try yourself. So the first one, express ln of 125 in terms of ln of 5. Well, ln of 125, we know that 125 is 5 cubed. Okay? But that's equal to 3 ln of 5. Because whenever you have a power inside of your logarithm, you can bring it out front as a coefficient. Okay, the next problem, expand into logarithms of simpler terms. So the ln of cosine of x divided by x cubed, well, the ln of a quotient is the difference of the ln's. So ln of cosine x minus ln of x cubed. And if we want to simplify that further, ln of x cubed, again, we can use that the power goes in front as a coefficient. So ln of cosine x minus 3 ln of x. Okay. Finally, combine into a single logarithm. 3 ln of x minus 1 minus 1/2 ln of y squared plus z. Okay, so we want to combine this into a single logarithm, but it's hard to do that when we have these coefficients. So let's use the power relationship to put the coefficients inside of the log. So 3 ln of x minus 1 equals ln of x minus 1 cubed. Okay, that's the first thing. 1/2 of ln y squared plus z is equal to ln of the inside raised to the half power, which we can also write as the square root of y squared plus z. Okay, putting this all together, we have the ln of x minus 1 cubed minus ln of square root y squared plus z. The difference becomes the log of the quotient. So we have that the answer is the ln of x minus 1 cubed divided by square root of y squared plus z. Okay. So these are a few types of manipulations with logarithms that you should be comfortable with for this semester. Okay, completing the square. So this might be something you haven't done in a while, which is fine. It's more common earlier in the math sequence, but it's going to have some use for us later. For a quadratic polynomial, quadratic means degree 2, of the form x squared plus ax plus b, completing the square is putting the quadratic polynomial in this form. So the first part is just showing you how you're splitting up the x squared plus ax with plus a squared over 4, and then you're putting the b by itself. Let me make this more explicit. So really, this is from the original expression, and this is from the original expression. And these two things, adding them, these cancel. So that this is really just the same thing as what's above. Okay? But the great thing about this is that the first expression factors as a square, and the second expression has no x. Okay, so this is a square, and this is constant. Okay, and we're going to use this a lot later. Okay, so let's see how this can be applied in a simple example of solving a quadratic equation. So let's say we have x squared plus 2x minus 3. So we want to write this in the form of completing the square. So we take 1/2 of a, so that's 2 divided by 2, which is 1. So a equals 2. So this becomes 1. And then we take plus -3 minus 1. Okay, and that's, so this is the same polynomial as above, so the equation still holds. Then this is x plus 1 squared, right? That's how you factor this first term, minus 4 equals 0. Okay, we can put the 4 on the other side. We have x plus 1 squared equals 4, which means x plus 1 equals plus or minus 2. Okay, because those are the two things whose square is 4. And that means that x is equal to either -3 or 1. Okay? So that's an example of using completing the square to solve a quadratic equation. Okay, and this is the way that we'll usually encounter this in this class. We'll have a polynomial in some expressions, usually in some integral, and we'll want to write it as a sum of squares. So we can write 4x squared minus 12x. Well, to do completing the squares, we usually like to have the coefficient of x squared be 1. So let's just factor 4 out. Okay. Now we want to write x squared minus 3x as completing the square. So we can take x squared minus 3x. Okay, well, a is minus 3. So that means that we're adding 9/4. Okay, because it's a squared over 4. And because we add 9/4, we also have to subtract 9/4. In this case, the constant term is 0, so that's the only thing we have to consider. And this, in turn, is equal to x minus 3/2 squared minus 9/4. Okay, and then when we take the 4, so bringing in the 4, we have 4x squared minus 12x. That's equal to, when we put the 4 inside of the square, it becomes a 2. So this is 2x minus 3 squared minus 9. Okay, so really this should be, instead of the sum of squares, this should be the difference of squares. Okay. Now we're going to talk about polynomial long division, which you probably did at some point in the algebra sequence. This is also something that's going to come back up when we do partial fractions. So given a rational function, f of x over g of x, that means a quotient of two polynomials, where f is a polynomial and g is a polynomial, we can express it as a sum q of x plus r of x over g of x, where r of x has a degree less than or equal to the degree of g of x. And recall that the degree of a polynomial in one variable is the largest exponent that appears. Okay, so if it's x cubed plus x plus 1, okay, that 3 is the highest exponent, so that's the degree of the whole thing. Okay, so I could give you an algorithm, like a list of steps for how to do polynomial long division, but it's much easier to understand just by doing an example. Okay. Compute x cubed plus x squared plus x plus 1 divided by x plus 2. Okay, so the way that we do this is we set up our division bar. Okay, and we write x cubed plus x squared plus x plus 1. And on this side, we write the denominator, which is x plus 2. Okay, now at each step, excuse me, you take the leading term and you see what you would have to multiply by the leading term here to in order to get the leading term over here. So x, we want to multiply by something to get x cubed, so that's going to be x squared. Okay, and we multiply each term by the x squared, so we have x times x squared is x cubed, plus 2 times x squared, that goes under the x squared term here, and then we subtract. Okay. So now we have negative x squared plus x plus 1. Okay, and now we do the same thing as before, except now this is our leading term, including the minus sign. Okay, so what do you have to multiply x by to get minus x squared? It's going to be minus x. Okay, and you do the same thing as before, multiplying through, minus x squared minus 2x. Okay, and subtract. The minus x squareds cancel. We have 3x plus 1. Okay, and we do this one more time. We have our leading term here is 3x, and we again are looking to multiply x by something to get 3x, and that's going to be 3. And we multiply through, we get 3x plus 6, we subtract, let me put parentheses over here too, and we end up with minus 5. Okay, so in terms of an answer, so the answer to this problem would be x squared minus x plus 3 minus 5 over x plus 2. Okay, we could say plus negative 5 over x plus 2. Okay, and that would be a simplification of this expression. Let's do one more example. This is a little trickier because not every monomial is represented. So when we do this division bar, we have x cubed. We have to put in placeholders for the x squared and x, plus 0x squared plus 0x plus 1. Okay. This actually is not such an interesting example. So let's make it a little more interesting by putting in 1 here. Or let's put in an x plus 1. Here we go. That should be more interesting. Okay. X squared plus x plus 1. And we're going to divide x squared into x cubed. You need an x to get there, so then you get x cubed plus x squared plus x. Subtract, and we end up with minus x squared minus x plus 1. Okay, doing the same thing as before. Now it's minus 1 that goes into here. So we get minus x squared minus x minus 1. Subtract through, and you get 2. Okay, so x cubed plus 1 over x squared plus x plus 1 equals x minus 1 plus 2 over x squared plus x plus 1. Okay. Thanks for bearing with me with that example. Okay, now we'll look over some derivative rules that should be familiar. This is product rule. The derivative of a product f times g is f times derivative of g plus g times derivative of x. So for instance, if we want to take the derivative of this function, which is e to the x times cosine x, well, we'll take f to be e to the x. And so in the first term, we're going to have dg dx, which is just the derivative of cosine x, which we know to be minus sine x. And g is cosine x times the derivative of e to the x, which we know is just e to the x. So this is going to be e to the x times cosine x minus sine x. Okay, that's an example of the product rule. Okay, quotient rule. It's a little more complicated. It feels a little less complicated if you think of it as just product rule with f times 1 over g, and then it makes a little more sense. It's kind of a combination of the product rule and the chain rule. Okay, so derivative of f over g is equal to g derivative of f minus f derivative of g divided by g squared. Okay, so I gave a little bit of a tricky example here. Derivative of tangent of x. But this is actually something we can do with the quotient rule because we have, this is really sine over cosine. Okay, so with f equal to sine x and g equal to cosine x, we can fill in the formula. So the derivative of tangent is equal to cosine x times the derivative of sine x, which is cosine x, minus sine x times the derivative of cosine x, which is minus sine x. And all of that will be divided by, all of that will be divided by the square of the denominator, so that's cosine squared x. Okay. What's cool is that this term, there is a trigonometric identity that cosine squared x plus sine squared x equals 1. Okay. So for this reason, this is equal to 1 over cosine squared x. Or that's also written as secant squared x. Okay. Okay. All right. Let's look at the next slide. Okay, now this is the chain rule. The derivative of f of g of x, okay, where the input of f is g of x, is equal to f prime of g of x times g prime of x. Okay, so let's say we want to take the derivative of cosine cubed of x. Well then, f is equal to x cubed, and g is equal to cosine x. So what we would get is that the derivative of cosine x cubed is equal to f prime, so that's 3x squared, but you input g of x, so it's 3 cosine of x squared, times g prime of x, that's the derivative of cosine, which is minus sine x. Okay? All right, the next thing I want to review is the fundamental theorem of calculus. And there are two formulations that will be useful for us. One formulation is if the derivative of capital F is lowercase f, then the integral of from a to b of f of x, there should be a dx in here, is capital F evaluated at B minus capital F evaluated at A, which is pretty cool because instead of adding up the area under a curve over this whole interval, all you have to do is evaluate this function at 2 points. It's a pretty powerful statement. Alternatively, the derivative of the integral from a to x of f of t dt. Okay, so now we're thinking about this as a function of the last endpoint. Okay, so if we have this curve, let's say this is f of x, or rather f of t, and then this is x, okay, and this is some fixed a, and you're curious how fast is the area under this curve changing? Well, what the area picks up as it changes is just this little sliver over here, which is proportional to the value of the function. That's the idea. That's why the derivative is f of x. Okay? Okay, so let's use the fundamental theorem of calculus to compute these, to answer these examples. And again, feel free to pause. Okay. Compute the derivative of the integral from 0 to x of sine x dx. Okay. So again, oh, and this is a disaster. This should be sine of t dt. Okay, because once you're taking the x as the bound of the integral, it can't also be the variable that you're integrating with respect to. Okay, so once you do that, the derivative of this integral is just sine of x, okay, not sine of t, because what you're interested in is the variable here. Okay, that's where this integral ends. This is the right endpoint of the integral, and the rate of change of that integral is sine x. Okay. All right, now the more traditional application of the fundamental theorem of calculus. If you have the integral from 0 to 10 of x cubed dx, well, this integral is given by looking at the antiderivative. So the antiderivative of x cubed is equal to x to the 4th over 4. And the reason this is the antiderivative, or an antiderivative, you can really say plus c, but the constant won't matter here because we'll be subtracting. The reason this is the antiderivative is because when you take the derivative of this, you bring down the 4 over 4 cancels, and you're left with x cubed. That's what we're looking for. So that's why this is the antiderivative. So all we have to do is evaluate that at the two endpoints. So this means that the integral from 0 to 10 of x cubed dx equals 10,000, over 4 minus 0 over 4, which is 2,500, I think. Okay, now we're left with the final topic I wanted to discuss today, which is u-substitution. Given an indefinite integral of the form integral of f of u of x times the derivative of u with respect to x dx, we have this equation where instead of that first integral, we can just look at integral of f of u du. Okay, we're treating u as a variable now. Okay, this is our new variable. And it may be simpler to compute. If the integral is definite, the same equation holds, but you also have to change the bounds. Okay, so you'll note here, you evaluate u at the, you evaluate u at the two bounds. Okay. So let's see this in action. So here we have u, so the inside of the exponential is x cubed. Okay, and if we wanted to see if this has the correct form, we need to know what du dx is. So this is 3x squared, okay? So we're almost there because we have x squared e to the x cubed dx. So we can write this as, this is 1/3, okay, and the 1/3 is going to cancel out a 3 that I add in. 1/3 times e to the x cubed times 3x squared dx. Okay, now we have the derivative of u with respect to x and f of u, and we can make the substitution. 1/3 times the integral of e to the u du, which is just 1/3 e to the u. Subbing back in, this is 1/3, sorry, let's be strict here. We should give this a constant of integration. And then this will be 1/3 of e to the x cubed plus c. Okay, so that's one application of u-substitution. Here's one with, my apologies, this should be some other integer. Let's make this, why not 3? Okay. I think I wrote in the wrong example here. So let's correct this a bit. We're going to make this the integral from 2 to 3 of x times root x squared plus 5 dx. Okay. So, given this integral, I'll cross this out. Given this integral, we have, okay, the thing inside of the square root is going to be our u. So that's x squared plus 5. And du dx is 2x. Okay. So this is equal to the integral of, now I'm evaluating u at the endpoints. So this is 9 and 14. Okay, because when you plug 2 in, you get 2 squared plus 5 is 4 plus 5 or 9. And 3 squared plus 5 is 9 plus 5 or 14. And then we pick up an extra 1/2 because we have a 2x over here, so we needed to get this from somewhere. And this is the square root of u du. Okay. And when we take this integral, this is an application of the power rule of integration. We get, instead of u to the 1/2, we have 2/3 u to the 3/2. Okay, and we're evaluating that from 9 to 14. So that gives us, well, the 1/2 times 2/3 is just 1/3, which is nice. And we have 14 times the square root of 14 minus 9 times the square root of 9, which we actually know this one, this is 3. So we can take this as 1/3 14 root 14 minus 27. Okay. And one final example for us. Yes, this is an example. So this is another tricky application of tan. So we can look at this as the integral from 0 to 1 of sine of x over cosine of x dx. Okay. Now here we know that cosine, its derivative is sine, okay? And cosine is inside of this reciprocal function. So we're going to let u be equal to cosine of x. And du dx, excuse me, this is equal to minus sine x. So this becomes minus the integral 0 to 1, 1 over cosine x times minus sine x dx. And this is equal to minus the integral, and we have to actually sub in the u values. So cosine of 0 is 1, and cosine of 1 is some irrational number. And then we have 1 over u du. Okay. So this is going to be equal to minus ln of the absolute value of u from 1 to cosine of 1, which is equal to minus ln absolute value cosine 1 minus negative ln 1. Okay, and we know that ln of 1 is 0, and we also know that cosine of 1 is positive because it's less than pi over 2. So we get minus ln of cosine of 1. Okay, and that's our definite integral here. Okay, and I appreciate you bearing with me. Still getting used to the technology with the tablet. I'm going to post these slides, and we're going to do some problems related to these ideas in our group work lecture.